Have you ever wondered how computers work? Traditional computers work using bits which are either zeros or ones. But there's a new type of computing that is shaking up the industry: quantum computing. Quantum computing uses a completely different approach to traditional computing. Instead of bits, it uses qubits. Quantum computing is a type of computing that uses quantum bits or qubits instead of traditional binary bits used in classical computing. Qubits can exist in multiple states simultaneously, allowing for much more complex calculations to be performed much faster than with classical computers. One example of a calculation that can be performed much faster with a quantum computer than with a classical computer is factoring large numbers. Factoring large numbers is a crucial component of many encryption algorithms, and breaking such encryption is a difficult task for classical computers. However, with a quantum computer, Shor's algorithm can factor large numbers exponentially faster than classical algorithms. This means that quantum computers can potentially break encryption that is currently considered secure by classical computers, which has important implications for cybersecurity. In a classical computer, a bit is either 0 or 1. In a quantum computer, a qubit can be in a state called superposition, where it is both 0 and 1 at the same time. This is because, at the quantum level, particles can exist in multiple states until they are observed or measured, at which point they collapse into one of the possible states. To illustrate this, imagine a qubit represented by a sphere. In a classical computer, the sphere can only exist at either the North Pole or the South Pole. However, in a quantum computer, the sphere can exist in any point on the surface of the sphere, representing a superposition of both states. This allows quantum computers to perform many calculations simultaneously, giving them the ability to solve certain problems that are too complex for classical computers to handle. So, a qubit can be in a state that is a combination of 0 and 1 at the same time, known as a superposition state. This allows quantum computers to perform multiple calculations simultaneously, exponentially increasing their processing power compared to classical computers. Quantum computers use a process called quantum entanglement, which allows two or more qubits to be connected in a way that the state of one qubit affects the state of the other qubits. Quantum entanglement is a phenomenon where two or more qubits become linked in a way that their states are correlated. When qubits are entangled, the state of one qubit is dependent on the state of the other qubit, no matter how far apart they are. To understand this, let's consider an example of two qubits that are entangled. If we measure the first qubit and observe that it is in the state 0, we know that the second qubit will be in the state 1. Similarly, if we measure the first qubit and observe that it is in the state 1, we know that the second qubit will be in the state 0. This correlation between the two qubits remains even if they are separated by a large distance. One of the most famous examples of quantum entanglement is the EPR paradox, which was proposed in 1935 as a thought experiment to highlight the strange and non-intuitive properties of quantum mechanics. The EPR paradox involves a pair of entangled particles, such as two photons. When one of the particles is observed, its state collapses into a definite state, and the state of the other particle is also determined instantly, even if it is located on the other side of the universe. In quantum computing, entangled qubits are used to perform operations that are impossible with classical computing. For example, entangled qubits can be used to perform quantum teleportation, which allows quantum information to be transmitted instantaneously over long distances without physical transport of particles. Entangled qubits can also be used to perform quantum error correction, which is crucial for the reliability of quantum computing since the fragile nature of quantum states makes them prone to errors. Overall, quantum entanglement is a fundamental aspect of quantum mechanics and is essential for many applications in quantum computing and quantum communication. Quantum computing has the potential to revolutionize many industries, from finance to healthcare, by allowing for faster and more efficient calculations. However, building a large-scale quantum computer is still a significant technological challenge and requires highly specialized knowledge and equipment. Despite the challenges, researchers and companies are continuing to invest in the development of quantum computing technology. In the future, we may see quantum computers being used for things like predicting weather patterns, modeling complex chemical reactions, and even creating new materials. The potential of quantum computing is huge and the possibilities are endless. Thanks for watching.